So if you recall, we talked about transformers last time and the ideal transformer. Basically, we explained about how voltage is produced. If there are two windings on the transformer, one side is connected to a source, the other side to the load. And we also explained about the dot convention. That was a way that without opening the box of the transformer, we could understand how the flow of current on the secondary side would be based on the dots. So dots would be associated with the terminals of the same polarity. And if we are considering a relationship in the ideal transformer based on EP over ES is IS over IP, then if the current goes into on one side, the current goes into the dot, the current should come from the out of the other dot on the other side so that this relationship holds. If not, if one of the currents is reversed, then this relationship would have to get a minus sign in front of it. And then we talked about the impedance transformation. So in the ideal transformer, the impedance that we see from the perspective of the primary and the secondary would be different, and that would be based on ZP over ZS would be the square factor of NP over NS. Now let's go to a more realistic model of a single-phase transformer. So we're adding these components to the side of the ideal transformer on the two sides in order to make it a more realistic type of transformer. These components are in the form of resistances and reactances. The ones that I'm showing with RP, XP, RS, and XS would be called the series impedances. And RP and RS are showing basically the losses on the windings on the primary and secondary sides, respectively. And the X's are basically showing the leakage reactance associated with the windings on the primary and secondary sides. We have two admittances in here, which are called the RC and XM. The RC is standing for the core losses in the core, and XM is basically related to the fact that our core is not an ideal core. If our core was an ideal core, then this XM would have been infinite, which means that this would have been an open circuit. But since our core is not ideal, then we take this XM as the magnetization reactance. So this is the core, RC, representing the core losses, and XM representing the magnetization reactance of the transformer. Keep that in mind that whatever we have in here, in the what I call the ideal portion of the transformer, would be the same thing that you had for the ideal transformer. So it means that EP over ES would be the same as NP over NS, would be the same as IS over IP, right? Repeat that. EP over ES would be the same as NP over NS, would be the same as IS over IP. But beyond that, the relationship between VP and BS would really depend on these impedances and how much currents are flowing into these basically extra parts of the transformer. So VP over VS will not be the same as NP over NS, but EP over ES would be the same as NP over NS. Just keep that in mind. So this IX would be called the magnetization current. And since this current is IP and we have this IX as a magnetization current, the current in this primary side path would not be the same as IP. So that's why I call it JP. There's a little bit of difference between JP and IP. If I have an ideal core, meaning that both of these two, resistance and reactance, if they would be infinite, then JP would have come equal to IP, right? There would be no leakage of current in here, in this magnetization path. So we can use the KVL and KCL in order to analyze a real transformer based on the components that have been, the values that have been provided to these components. Let's look at one example here. Example 4.1. We have a 250 kilovolt amp single-phase transformer. And when we say that 250 kilovolt amp, that means the rating of this transformer. This transformer can take up to this much in terms of apparent power. So this KVL is generally a combination of active and reactive powers together in the form of apparent power. We have nominal voltages of 2000 volts and 200 volts in its primary and secondary sides, respectively. So this means that 200 volt and 200 would be the same ratio as the NP over NS. So when we describe a problem like that, 200 over 2000 over 200 is the same as NP over NS, which we called it as alpha. So in other words, alpha is 10. The primary series resistance and reactance are 0.10 and 0.5 ohms, and the secondary series resistance and reactance are 0.001 and 0.005 ohms. So this is RP, this is XP, this is RS, this is XS. The shunt impedance of the transformer can be modeled with a resistance of 8,000 ohms. So this is RC, in parallel with a reactance of 1,200 ohms. So this is XM, right? See that usually the series impedances are way lower compared to the shunt impedances. So in ideal conditions, these series impedances should be zeros, and these shunt impedances should be how much? Infinite. So all of these, these numbers, the 8,000 and 1,200, are both referred to the primary side. So that means that these are referred to the primary side. And these values, the 0.1 and 0.5, RP and XP is referred to the primary side. RS and XS is referred to the secondary side, and RC and XM are also referred to the primary side. That's because we know if we go from one side to the other side, that the impedance will also transform based on NP over NS squared. A load is connected to the secondary of the transformer at the rated voltage. So a load is connected here at the rated voltage. What is the rated voltage? On the secondary side, that's 200 volts. If the load is consuming the rated apparent power, which means this much of apparent power, at 0.8 lagging power factor, we want to use a step-by-step procedure to find out VP. And then after that, write up a MATLAB script to evaluate VP. Okay. So we start from where we know where the knowns are, which is on the load side. On the load side, we know SS, right? So let's call SS the apparent, the complex power. The complex power on the secondary side or on the load side, which would be equal to the apparent power, which we have how much? 250 kilovolt amps. So this 250 kilovolt amps gives you the magnitude of that complex power. But that complex power really has an angle also associated with that, which comes from the power factor information. So the power factor is how much? 0.8 lagging. So therefore, the angle of that apparent power would be, since we are having a lagging power factor, we need to put a plus sign of our cosine of the power factor, right? Our cosine of 0.8. So this gives you the information associated with the complex power in here. If I had told you that we have a leading power factor, then you should have put a minus sign in here instead of the plus sign. Okay, so this is the first step. We find the SS, and if this is your load, and this is the SS that it's consuming, this was plus minus V secondary, or V of the load, and this was the I of the secondary, the current through the secondary side of the transformer. So from, because we have VS, VS is equal to how much? The rated value, which is 200 volts on the secondary side. We have to adopt a reference of angle at the point that we have the knowledge of the voltage. So because the voltage at this point has been given to us, this means that we could say VS bar is 200 with the angle of 0, which means that this point serves as the reference of angle for our problem. This point, right? So we get this. Now through these two values, SS and VS, we can find out the IS. So how do you find that? We know IS is the conjugate of SS over VS, right? So we get IS. Now I can go back to this figure. When I have IS, then I can find out the voltage drop in here, which through this KVL in this path would give me ES. So therefore, I can say that ES would be equal to VS plus RS plus JXS times IS, right? So this gives me ES. Since I have ES and I have the NP over NS ratio, I can find out EP. So I know that EP over ES must be the same as NP over NS, which for me is the same as 2000 over 200, or equal to 10. This should be giving me now EP. EP should be equal to 10 times my ES. And using the reciprocal information, I can find out IP. So IP should be this 1/10 of now IS. So I get both the EP and IP. EP and IP. Now, since I have the knowledge of EP, the same voltage is falling on these two impedances, RC and XM, right? Therefore, I can find out, I can get a combination of these two as an impedance and then find out the IX. Or I can individually find out IC and XIM because both of these are in parallel with EP. So let's do it that way. So IC would be EP over RC, and your IM would be the same as EP over JXM. Don't forget the J. And these two together become IX. So your IX becomes IC plus IM. You can find IX. Once you find IX, then through KCL, you can find JP. Your JP would be IX plus IP. So therefore, your JP would be your IP plus IX. And then it should give you the knowledge of this voltage drop, which can give you VP through the KVL that you can write here in this loop. So therefore, your VP would be found from EP plus RP plus JXP times JP. So this can give us all the information that we need in the problem. Now, in extra to what was required, let me ask you a few more questions in here. Can you give me the complex power that is sent by the source? So if the source is connected here, how much complex power would be sent by the source? VP times conjugate JP, correct? So S on the primary side would be VP times JP conjugate. Can you give me an easy impression for the efficiency in this transformer? So if you have like S on the secondary side, the complex power of the load was VS times IS conjugate, right? If you just get the real parts of each of these, so your P would be the real of SP, and your PS, which is the same as the P of your load, would be the real portion of SS. So your efficiency would be PS over PP. If you want to express that in percent, that would be times 100. All right, so we talked about the transfer of impedance between the two sides. So this means that instead of representing the transformer model based on the two sides, you can refer things from the primary side to the secondary side or vice versa. But while doing that, you have to basically consider the right transformations, the right transformation coefficients. So by transforming things from one side to the other side, what happens is that this ideal part just vanishes. This becomes just 1 point. So like here, the ideal portion, we just eliminated that. We kept the values on that were on the primary as is, no change. The ones that were basically coming from the secondary referred to the primary side, take primed values. Okay, so this means that practically speaking, what I'm going to do is I just delete this part. You can see that IP becomes equal to IS, but since IS is coming to the primary side, this becomes IS prime. Our S and X, S and VS also become primed values. So this is the model referred to the primary side. We can do the same thing referred to the secondary side, which means that we can keep all the values and parameters that on the secondary side as is, but take whatever was on the primary side to the secondary side and rename them as primed values. And there is a certain relationship between these primed values and their original values based on the turns ratio of the transform. So in here, we also see that by not only IP, when we refer the model from the secondary to the primary side, not only IS prime becomes equal to IP, but also ES prime becomes equal to EP. So how do you write that? ES prime is equal to EP and is really based on the turns ratio of the transformer, which is NP over NS times ES, or A times ES. For the currents, that's the reciprocal, basically, relationship. So that becomes NS over NP times IS. So for the impedance, that's the same format as the turns ratio with a square factor. When we transfer impedances, do not forget the square factor in here. So that's the same way that, so is if voltages are going to increase, impedance is going to increase too with a square factor. But the current would need to decrease. So keep that in mind. One easy way to remember this is if you want to transform voltage. So we say, for example, ES prime would have of ES times the side to which it goes to. So what is the side to which it goes to? Yeah, so ES prime means something was in secondary, we referred that to the primary. So whatever it goes to, you put it on the numerator. Whatever it's existing still, you took it to the, you put it on the denominator. So NP over NS. So let's do that for EP prime. EP prime would be E prime times the side to which it goes to is secondary now over NP. The relationship with current for currents would be reversed. So this means that IS prime is IS times NS over NP. And IP prime, so these are separate things. IP prime would be IP times NP over NS. For the currents, that's the other way. For the impedance transformation, it would be similar to the voltage with a square factor. So this, in other words, whatever was on the secondary goes to the primary. So for example, if you had XS, which was on the secondary, you take it to the primary, that becomes XS prime. That would be same as XS time NP over NS. Do not forget the square factor. So with the same logic, let's say if I want to have RC prime, what should I put in here? RC prime was belonging to the primary, right? Now it's going to the secondary. So the side that it goes to would be NS. The side in which it is, which is NP, with a square factor. Yeah, you can see all of these relationships in here. You don't have to memorize this, but if you memorize this rule, it would be really easy. Now let's go to transformer approximate models. Let me go to this realistic model, which was referred to the primary. You can see that in the problem that we solved, the values of these series impedances, RPXP, RS, and XS, usually were much, much smaller than RC and XM. Okay? This means that if instead of this circuit, I put basically RS and XS, RX prime, S prime, and XS prime, remove them from here and put them in series with RP and XP, then there won't be a lot of error in my final calculations, usually. Okay? So if it makes sense, my life easier, we can, depending on how much basically these values are way bigger than these, we can basically combine these two series impedances together, refer them to one side and combine them together. So again, this is like an engineering judgment. So let's say if these values are in the order of like 1, 2, 3, 4, and then this was 5 and 6, then this is not a good approximation, because 5 and 6 are very close to like 1, 2, 3, and 4. They are in the same order, right? But if instead we had 1, 2, 3, and 4 here on the series side, and this was 5,000, 6,000, then we have the more 1,000 order difference, right? So therefore, it would make sense to just combine them together from one side to the others. So as engineers, you really need to be able to make these approximations under different circumstances. This usually in the case of power systems, that's the way that we can do that. So same thing in here. So if you can look at here, this is basically the way that we found an approximate model of the transformers by referring the series impedances on the secondary side, transforming them to the primary side, and then combining them with this primary side series. So this, in other words, this RSE is really equal to RP plus the RS that has been transformed to the primary side. So RP plus RSP. And this XSE would be same as XP plus XS. And this one is an example of when we combined everything, the series impedances on the secondary side, which means that we brought them from the primary side, transferred them to the secondary side, and then combined them with the secondary side. So RS plus RSE here becomes RS plus RP prime, and XSE would become XS plus XP. This doesn't mean that we always have to do this. We can do these types of combinations if they make our calculations easier. So back in older days where there were not a lot of basically computers, you had to do a lot of calculations by hand, then it would make sense to do these types of approximations. But nowadays, if you really want to do them more accurately, you have computers in hand, which you can do that much easier using like a little code or script that does all that for you. So this is just a historical perspective of back in older days, we wouldn't make a lot of error if you did basically these types of approximations. And last but not least, we talked about the fact that these two impedances are very big. So why not just assume that they're infinite, which means that they would be vanished, right? We just ignore it. In most power systems, bulk power systems like transmission line transformers, we pretty much ignore the shunt part without a lot of basically error. Because what is important for us is really the relationship between VP, JP, VS, and IS, which in the case of large-scale bulk transmission transformers, it really doesn't matter that much if you want to include this or not. You wouldn't make a lot of basically mistake. All right, so again, let's go through some examples in here. We want to have an approximate model, which has been combined in the primary. So the same problem, example 1 that we just did, we want to repeat the same problem, considering an approximate model of 4, 6. So in this figure, you can see that we have combined the series impedances on the series side, transformed them to the primary side, and combined them with the primary side, right? So if you recall, we started the problem from the secondary side because we had the information associated with the load available to us. On the secondary side, we had the voltage of the load and we had the power, complex power of the load. So we calculated IS. So from here, you can easily say that VS is equal to VS, and IS also would be transferred to IP, and ES would be transferred to EP through the right, basically, in the application of the transformers turns ratio. So you can find IP and EP, and then the rest of the problem from here would be similar to the problem that you did in the previous part. So you can see that in the previous problem, when we have this model, you found basically IS, but you had to calculate for this voltage drop once in here and once in here. But in this problem, based on this model, now you're not calculating that voltage drop twice. You just do it once in here. And as you can see, by doing that, VP would be found at this value, which compared to the value that you calculated in example 4.1 has less than 0.04% error. That's a really small error. And then approximate model combined in the secondary, if you're using for the same problem, if you're using an approximate model based on figure 4.7, now you have to do the voltage drop only once in here and not on the primary side. So if you do so, you get the voltage at this value, which again, with respect to the original problem, which was the most accurate model, has an error of less than 0.043%. Now let's go to see how you can evaluate the parameters of the transformer in lab through experiments. We want to find out the RSE and XSE, which is the combined basically series impedance of the transformer between the primary and secondary sides, as well as the RC and X. So we do two experiments. The short circuit experiment is supposed to give us the RSE and XSE. Consider this figure 4.8. Look at this figure 4.8. This is an approximate model. Our goal is to find out our SE and XSE based on an experiment. So what we do is to apply a short circuit in here, short these two terminals, and then put a varying voltage source in here, start to increase the voltage from 0 all the way up to when you see the rated current flowing through the primary circuit. You don't want to put a large voltage in here, because if you put a large voltage, you will damage your transformer because it's shorted. You just want to increase the voltage on the primary side until you reach the rated current. So how do you find the rated current? From the nameplate of the transformer. If your transformer nameplate is 260 kVA, that's the S, right? And if they say that VP is 2000, VS is 1000, then how would you find IP rated? So I say VP rated. I put R just for rated because it's hard to read right on this. VP rated, VS rated. This is S rated. So how would you find IP rated? So basically, S rated should be equal to V rated times I rated. Simply speaking, right? In terms of S, when you put basically complex power, then you have to put basically bars and put the conjugate and all of that. But as long as we're dealing with just the apparent power and the voltage and current magnitudes, then this is correct. So SR would be VR times, which means that that should be correct for both primary and secondary sides. So we have S rated equal to V primary rated times I primary rated. So from here, you can find I primary rated to be equal to S rated, which is 260 kilovolts over 2000. This is kVA. S should be kVA, not K. And this is like, let's say it's, if this was volt, then you should not forget this becomes how much? Kiloamps. Whatever you get is kiloamps. So this would be the rated current on the primary. So we just increased the voltage on the primary until we experience 0.13 kiloamp, or around how much? 130 amps, not more than that. Otherwise, you would damage your transformer. And then our goal was to find out RSE and XSE. So first of all, we see that in terms of the magnitude of the impedance of the transformer, that ZSE would be VSC over ISC. If the voltage is at VSC, the current is at ISC, then this would give you basically the ratio of those, would give you the ZSE. And then also apply a watt meter in here. Not only put a voltage source, but also put a watt meter and measure the watts. How much power is going to be consumed? That power has a relationship. The only element that is consuming power in the circuit would be this RSE, right? So therefore, the power would be RSE times ISC squared. So this gives you ZCSE, this gives you RSE, but you're still required to find out XSE, which would be the square root of ZSE squared minus RSE squared, because we know ZSC is RSSE plus JXSE. So therefore, we can find out XSE as square root of ZSE squared minus RSE squared. So through 3 simple steps like this would give you basically the RSE and XSE values. This is called the short circuit experiment. The next step would be the open circuit experiment, in which our goal is to find out the RC and XM. So for that purpose, we go to figure 4.7. Let's go here. Now, instead of having a short circuit, let's keep the secondary open. If you keep the secondary open, there would be no current passing through here, right? So there would be no voltage drop in this path. So whatever you had would be associated with this path. So keep the voltage open. Now you can apply the rated voltage on the primary because you're not shorted now. You are open on the secondary. So apply the primary nominal voltage on the primary and get that current measured as well as the power measured. Power needs to be measured in here. Keep that in mind that your wattmeter should be a really delicate wattmeter in here because you're open circuit. Therefore, the amount of power that is going to be consumed through this path would be very small. So it's really important that you have a good wattmeter, which sometimes they call it compensated wattmeter. Those are the types of wattmeters that are more expensive and are basically they have extra components to account for the inaccuracies in the measurement. So the process here would be that, first of all, through that P open circuit that you measured and V open circuit that you applied, the RC can be readily found because the POC is the power, the real power is only going to be consumed in this RC component, not in XM, right? So therefore, your RC can be readily found. And then you can find out IC by VOC over RC. And then the IM, the magnitude of the magnetization current, can be found from square root of IOC squared minus IC. That's because your IX bar is equal to IC bar plus IM bar. So therefore, that relationship for the magnitudes would be based on IX squared would be equal to IC squared plus IM squared. So through this, you can find IM, and then finally, you can find XM. So again, four simple steps to find out the equivalent parameters of your transformer. And here is an example that we have applied. Basically, remember these short circuit and basically open circuit tests could be theoretically applied at any site. You can apply it on the primary side or the secondary side. So here we have an example in which we are applying the open circuit test on the low side, on the low voltage side, and applying the short circuit test on the high voltage side of the transformer. So our transformer's nameplate is 200 kVA, 2000 volts over 500 volts, 60 hertz. So this is basically the information that is indicated on the nameplate of the transformer. Through experiments, we want to approximate the model, find the approximate model of the transformer. So first, upon the open circuit test, so the open circuit test was supposed to find out what values are RC and X. The short circuit test was supposed to find what values are SE and XSE. So if you're applying the open circuit test on the low side, the values that you find would be RC and XM referred to the low side. Also on the short circuit test, because you're doing that on the high side, the RSE and XSE that you will see or you will calculate would have been transferred to the high voltage side. Then depending on the problem statement, they might ask you to get all of those impedances referred to a specific side. So you have to be able to do that transformation as well. So through what I want in this problem is to find out the equivalent parameters referred to both sides. Being primary or secondary doesn't have anything to do with the high voltage side or low voltage side or the source side or the load side. It doesn't have anything to do with that. We just call it primary, call it secondary. That's it. The primary might be connected to the source, might be connected to the load. So a better way is really to say low voltage side versus the high voltage side. Each of these could be theoretically connected to source or load. Okay. So we know that when we say low voltage side, we know that it's been referred to the 500 volt side. When we say high voltage side, we know that it's been referred to the 2000 volts. So using the open circuit data, those 4 steps, I went through them, find basically RC and XM both referred to the low voltage side or referred to the 500 volt side. So this means that if I want to refer them to the high voltage side, then I have to do this transformation. So look at this value, 166.67 referred to low voltage side, but referred to the high voltage side, it would be 2,666 volts. Now, on the short circuit test, we're doing that on the high voltage side, which means that if you do the calculations, the values that you see for the RSE and XSE are referred to the high voltage side. So if you want to refer them to the low voltage side, then you have to transform them based on the turns ratio of the transformer.